Hello Performance Ninja and welcome to the Loop Interchange 2 lab assignment, where you will practice doing more sophisticated loop transformations. In the previous lab, which is called Loop Interchange 1, we were talking about the basic case of interchanging loops when they are perfectly nested. But sometimes it is possible even when the loops are not perfectly nested. In this lab, we will deal with such a situation. Consider the following code where we need to print the sum of all elements in each column of the table. For example, for the first column, we sum up 1 plus 1 plus 1 plus 1, which equals to 4. Natural way to do it, as expressed in the code below, would be to run through each column, accumulating the value from each row in that column, print it, and then go to the next column. But as we have seen in the previous lab, the memory access pattern is not optimal. We need somehow to change the way we traverse our table. Interchanging the loops right now is not possible. The code will simply won't compile. And we cannot flip the indices either, since it will be printing the wrong result. So we need to do something else here. Let's focus on the code now. Notice we have three phases inside the outer loop, which are sequential and depend on each other. We first need to initialize the value with 0, then accumulate the values and then print it. So how we can break this dependency chain? What we could do is we could not print the totals for all the columns right after calculating them, but instead we could save an intermediate result and then go to the next column. And only once we calculated the sums for all the columns, we go and print them. So that requires having not just a single temporary sum variable, but many. So for each column, we need to have an accumulator. Okay, so this is how we implement this idea, and let's move forward. Now it's possible to distribute the loop nest, since there are no cross-iteration dependencies. In other words, one iteration of the outer loop does not affect another iteration. Let's do this transformation. So here's how the code looks like after we distributed the loop nest. And only now, when the accumulation loop is perfectly nested, we can go and interchange those two loops for rows and columns. Okay, so we interchange the two loops. Now the memory access pattern is okay. We essentially transform the problem into a vector addition, which modern processors are extremely good at. The code becomes a little more verbose, but it will run much faster. So yeah, that's it for this video. You can now go to the lab assignment and try to improve the code.